Hello everybody and welcome to this new video on this channel. This time I'm going to show you how to plot a chirp signal in GNU Octave. In the last video we talked about sine waves, and a sine wave is a signal that has a single frequency in it. A chirp signal is a signal that varies its frequency over time. According to this variation over time, there are several types of chirp. For example, a chirp with a linear increase of frequency over time, or an exponential increase of frequency over time. Here we are plotting a chirp signal that increases its frequency linearly over time. So the chirp starts at a single frequency and then increases its frequency with a certain slope over time. This is what we are going to do this time in this video. And so yeah, again, let's start with the three common lines. We close each window that is maybe opened. We clear our workspace variables and we clear our command window. So, because we are in the digital domain, we need a sampling frequency, and let's set an arbitrary sampling frequency of 16 kilohertz. And then for the chirp signal, we need a start frequency and a stop frequency. Let's say we choose an arbitrary start frequency of 500 Hertz. And the chirp should increase its frequency linearly over time until it reaches the stop frequency of, let's say, 1500 Hertz, 1.5 kilohertz. So, this means that we are covering a bandwidth from 500 to 1500 kilohertz, so a bandwidth of 1 kilohertz. Bandwidth is the f1 minus f0, or maybe let's call them f-stop and f-start. Again here, f-start and f-stop. So, let's arrange them. So, okay, so our bandwidth is the difference between f-stop and f-start. Then we have to tell the chirp the amount of time that he gets to increase this frequency. So the overall duration of this signal. We call it t-chirp. Let's say we give him 125 milliseconds. So this is the time that the chirp needs to increase its frequency linearly from 500 Hertz up to 1.5 kilohertz. Therefore, the time is 125 milliseconds. So to plot our signal, we need a vector, a time vector. So let's call it t-vec. So our time vector starts at 0, and the increment between each sample is 1 divided by the sampling frequency. So this is the spacing between the time domain samples. And the vector goes up to t-chirp, because this is our overall time that we generate the signal. So now we have our t-vector, and now we will create our chirp signal. So we can create a chirp signal with the sine or cosine wave. I take the sine wave here because then our first sample will be 0, because the sine of 0 is 0. And so we generate the chirp like this: 2 times pi times f start times t. Don't forget the dot here because we have vectors. And this looks like a common sine wave, like we did it in the last video. And to generate the chirp signal, we add the term that the signal has to increase its frequency linearly over time. So we increase our frequency over a bandwidth, BW, that we set up here. So the difference between t-stop and t-start. And the time that he gets, or the slope of the increase, is the bandwidth divided by 2 times t-chirp. so the duration, and times t to the power of 2. Don't forget the dots here, because we want to calculate the power of 2 of each entry of the vector t-vec. It's t-vec, so not t. So that's why we need the dot here. And this dot we need it because we multiply vectors. So this is our chirp signal. Let's fire it up and see if we made any errors. Takes quite long. What's going on here with my... Oh damn. I see the failure. So the wrong sampling frequency was set. It's 16 kilohertz. I set it to 1.6 gigahertz. That's too much. So again, let's fire it up. Okay. So, and let's plot the signal to discuss about it. So we create a figure, and then we plot again our t vector against our signal. T vector will be the x-axis, and x will be our amplitude. So we name the labels. The x label is time in seconds, and the y label, let's call it amplitude in, well, let's say it's volts. It's okay. And then again I turn on the grid, because this looks much nicer in the plot. And then fire it up, and I will show you the plot window. So here we have our chirp signal. I have to... Oh, this banner here with the name of the video, I have to vanish it. So now you can see the whole plot. So x-axis is our time vector, and the y-axis is our amplitude of the signal. What you can see is that we have a signal here. We start at 0, because the sine wave of the sine of 0 is 0. Our t vector starts at 0. And then you can see that the frequency gets increased over time, starting from 0 to 125 milliseconds, which is our chirp duration, the overall duration of the signal. And what the chirp is doing, it starts at time 0 with the frequency of 500 Hz, and then linearly increases its frequency up to 1.5 kilohertz during the time from 0 to 125 milliseconds. The slope of this increase, we can... Well, wait here. So the slope of this increase, again, is this term here. BW divided by 2 times T chirp. So, but yeah, now we saw in the time domain signal, okay, we have here a signal that is increasing its frequency over time. But now let's have a look at the spectrum to see if we actually really cover a bandwidth. Therefore, to look at the frequency domain, we have to do the discrete Fourier transform, or what we do in an efficient way here in Octave, calculating the FFT. They produce the same output, DFT and FFT are the same. FFT is only a very efficient implementation of the discrete Fourier transform. So to calculate again the FFT, we have to tell GNU Octave or any other language that you prefer the length of the FFT, and here we take as length the length of the signal itself. So NFFT is the length of X. And to plot the signal, we need a frequency vector. Here in the time domain we created a time vector to plot our signal, the time vector against the time domain signal, and now we need to plot the frequency domain signal and a F vector. So, and this is minus NF. We start at the negative frequencies and we go up to the positive frequencies and normalize it. So this vector here now goes from the half of the sampling rate up to minus the half of the sampling rate up to the positive half of the sampling rate, covering the whole bandwidth, covering the whole frequency range. So now we have our frequency vector, we have our FFT length. Now we can calculate our FFT. I use again the letter X, but as capital letter, because it's common in math that the frequency or the discrete Fourier transformed signals are in capital letters and the time domain signals have their small letters. So it's really easy to calculate the FFT. It's the FFT command. We pass to the FFT command our time domain signal X and we tell the FFT command, hey, we want to calculate the FFT of length and FFT, which is the same as our signal length. So the output will be a complex signal here in X, but the FFT is arranging our frequencies in a way that we have first our positive frequencies and then our negative frequencies, and for plotting we want to have our negative frequencies on the left side and our positive frequencies on the right side. Therefore we use the command FFT shift to rearrange the complex output of the FFT command. So now everything is calculated and now we can plot our result. Again, we open up a figure and this time we plot our frequency vector FVec against our complex FFT output signal. And we plot it in decibel, meaning that we take 20 times the algorithm base 10. And because X is a complex signal, we need the absolute value of X. So we name our labels. X label is the frequency axis, so frequency in hertz. And our y-axis is the amplitude, but this time not in volts. We calculate it we name it in dB. And again we add our grid because the plots look nicer. Then we fire up everything. So then I have to show you the output. Here it is. So what do we have here? Here we have the spectrum of our generated chirp signal. What we can see here, we have here our frequency axis and we have here our amplitude axis in dB. Our frequency axis goes from half of the sampling rate. Our sampling rate is 16 kHz, so we start here at 8 kHz, minus 8 kHz, up to plus 8 kHz. We have here the negative frequencies and we have here the positive frequencies. We have a symmetrical spectrum because we have a real valued signal. It's a sine, or we could also use a cosine for generating the chirp, but it's a real signal and the real signal has a symmetrical spectrum. That's why we have here the negative frequencies and the positive frequencies. What else can we see here? So if we zoom in, we have a start frequency as defined in our Octave script from 500 Hertz. There we up somewhere here. And we told the chirp to go from 500 Hertz up to 1.5 kilohertz. And that's here. So we cover a whole bandwidth of 1 kilohertz. We can see it here. We don't see here the time that it takes to cover this bandwidth, but in the time domain plot we saw that our chirp is linearly increasing its frequency from 0 to 125 microseconds. Yeah. So what we could do now is we have here, as mentioned, a real valued signal with a symmetrical spectrum. Let's create a complex chirp to get rid of both of these signal components here and only show one of the signal components. Therefore we need a complex signal. Okay, let's do it. So again, let's go back to our workspace. And it's quite easy to create a complex chirp. Creating our complex chirp, we copy our wheel valued signal. Oh, only copy. So let's name it X comp for complex. And to create the complex signal, we have to replace the sine or cosine function with the exponential function. And we have to add the imaginary part, which is I or J, whatever letter you want to use. And that's all. So we only have to change the sign against the exponential command or the exponential function and add the imaginary part. So now we can again calculate our FFT. We have the same FFT length, we can use the same frequency domain vector. We only have to calculate again our FFT and we call it this time X comp for complex. So then again we pass our time domain signal X comp to our FFT command and tell the FFT the length that we want. And because the FFT output is arranged like positive frequencies and then negative frequencies, and we for our plots we want to change it, we again use the FFT shift command to rearrange the output of the FFT. And then we are finished. Then again we plot our result like with open up a figure. Then we plot again our frequency domain vector against our complex signal X comp. And we also want to plot it in decibels, so 20 times the logarithm base 10 and absolute value. So again our X label is frequency in Hertz and our Y-axis is again the amplitude in decibel. And we turn on the grid because it looks nicer. Then we fire up everything. So I will show you what is the output. Here it is. So here's the output spectrum of our complex chirp. So as we can see, we only have one frequency component, not a symmetrical spectrum. Here we only have the negative frequency part. We can also only create the positive frequency part by just changing the sign in our chirp function. So let's go back to our workspace, and here we have a minus. If we delete the minus and fire up everything again and then have a look at the output spectrum, we can see now our chirp spectrum is only on the right side, so only the positive frequencies. And again, let's check if we cover the bandwidth of 1 kilohertz. So we have our signal here. We start at, we told the signal to start at 500 hertz, and we are going up to 1.5 kilohertz. So it works. Everything works fine. And the problem of maybe if you are wondering why we do not hit exactly here 500 hertz or 1.5 kilohertz here, is because of the because we have a discrete signal here. We will talk about this phenomena in another video. But yeah, we cover a bandwidth of 1 kilohertz, and the time that we need, or that the signal needs to increase its frequency from its start frequency from 500 hertz up to 1.5 kilohertz is again 125 milliseconds. So the chirp signal is very important in engineering, because with such a signal you can test a device, or let's as an example let's take the audio domain. If you want, for example, to calculate your frequency response of an audio device, then you can fed a chirp into the device. The chirp is increasing linearly its frequency, and you can sample the output. And then you can see how what is the frequency behavior of your device over frequency. So it's a very good measurement signal. Or also in the field of radar you use chirps, because the cool feature about a chirp is that it spreads its energy over time. So you don't need that high peak powers, which maybe would break your amplifiers. Instead you can use a chirp signal and spread the energy over time. So, but that's only a very high level note. Yeah, I think that's it for this video. So now you should be able to understand how to generate a real valued chirp signal, a complex valued chirp signal, how to plot the signal, and how to calculate the FFT of the signal. And again, you should also understand the symmetrical spectrum of a real valued signal and the non-symmetrical spectrum of a complex valued signal. Yeah, that's it. Thanks for watching, and see you in the next video. Bye.